This question comes from Matt, who asks, what would happen if the moon were replaced with an equally massive black hole? And what would a lunar or polar eclipse look like? But it's actually an incredibly fascinating question that lets us explore the fundamentals of astrophysics. I won't spoil the answer just yet, but I will give you a small teaser later on. We will even have to resort to measuring temperatures in a unit called the mil-Fahrenheit, which should already hint at how surprisingly small the effect of a black hole moon would be on Earth. The conclusion may not be as catastrophic as you might initially expect. Now imagine a black hole with the exact same mass as the moon. If that entire mass were compressed into a black hole, in fact, it would only be about the size of a grain of sand. The event horizon of a black hole with the moon mass would be roughly the size of fine to medium sand grains, small enough that it could pass through a sieve labeled with ASM number 70 or larger. That's incredibly hard to visualize. Something with the gravitational pull of the moon, which moves oceans on Earth and stabilizes our planet's rotation. Of course, if such a black hole ever tried to pass through an actual sieve, when you compress mass into a black hole, you're not shrinking the mass itself, shrinking the radius at which escape velocity becomes equal to the speed of light. And once you reinside that, radius past the event horizon space, and time stop behaving in ways we can properly comprehend. Inside a black hole, the singularity is not a point in space as we normally think of it. For any object that falls in, the singularity becomes more like a point in time. It's neither here nor there in any spatial sense. It is instead the inevitable future of anything crossing the horizon. Since the moon's mass and orbital position wouldn't change, the Earth's motion, the way it orbits the sun, this is one of the fascinating quirks of gravity. As long as the mass is the same and remains in the same location, the gravitational field outside that mass doesn't care. So if the sun itself were replaced by a black hole of the exact same mass, Earth's orbit would be completely unchanged, would keep circling at the same speed and distance. The only difference would be that Earth would receive no sunlight, but mechanically speaking, the orbit would remain stable. In our case, with a moon-mass black hole, tides would rise and fall in the same rhythm as always. From the perspective of Earth's orbit and gravity, not much would be different. With the moon now compressed into a black hole, this means that the nights would suddenly become much darker. That lack of moonlight might not seem like a big deal to us humans. The absence of moonlight would drastically alter their behaviors and life cycles. Many animals use the brightness of the moon as a signal for hunting, mating, or migration. Still, when you compare this disruption to the many ways humans have already disturbed natural cycles on Earth, the effect of losing moonlight would be relatively minor. It would lurk there invisibly, detectable only by its gravitational presence. If the black hole were much smaller in mass, it would evaporate relatively quickly due to Hawking radiation, which is the slow leakage of energy from black holes predicted by Stephen Hawking. But a black hole the size of the moon's mass would actually absorb more energy from the cosmic microwave background radiation than it emits through Hawking radiation. This means it would be stable for an incredibly long time and wouldn't evaporate. Short, our black hole moon would really be black, completely invisible to the human eye, unless it managed to eat something. And that brings us to another fascinating point. If the black hole were to devour any object, say, a passing asteroid or a stream of dust, it would unleash an enormous burst of radiation. Black hole accretion disks formed when matter spirals into the event horizon. They can convert mass into radiant energy with an efficiency far greater than nuclear fusion. Luckily for us, there isn't much matter in the moon's immediate vicinity for a black hole to feast on. So in practice, it wouldn't glow very brightly. Most of its time would be spent subtly disturbing the orbits of nearby dust particles. In addition to the Earth getting darker at night, it would also get slightly colder. That's because moonlight doesn't just illuminate, it also contributes to Earth's energy balance. Measurements actually show that the global temperature fluctuates on a 28-day cycle, peaking slightly higher during a full moon. The effect is minuscule, mere fractions of a degree, but it is real. You might assume this warming comes entirely from visible moonlight, but that's not the whole story. The biggest factor is actually orbital geometry. The Earth is very slightly closer to the Sun during a full moon, because of the alignment of the Sun, Earth, and Moon. This means Earth receives a little extra solar energy at that time. That would still happen with a black hole moon, since its mass and orbit remain the same, so that contribution wouldn't change. Calculating the energy actually reflected and radiated by the moon is surprisingly complicated. The moon's phases mean it's not always reflecting the same amount of sunlight. And it turns out that when the moon appears half illuminated, it's much less than half as bright as when it's full. The moon heats up during the lunar day and radiates this stored energy back into space as infrared light during the night. Interestingly, the moon's infrared radiation affects Earth's temperature about 10 times more than its visible reflected light does. Even so, it's still about 10 times less significant, quantitatively speaking. Infrared moonlight warms Earth by about 1.2 milledegrees Fahrenheit. That's about 1.2 milledegrees Rankine. Without this contribution, the Earth would cool down ever so slightly. But considering the rate at which we are adding carbon dioxide to the atmosphere changing Earth's energy balance, on a global scale, this tiny cooling effect would be completely erased within a matter of weeks. Human-driven climate change far outweighs any lost infrared glow from a black hole moon. So, all in all, the conversion of the moon into a black hole wouldn't be that big of a deal in practical terms. Earth's tides would continue, nights would be darker, ecosystems would adjust, unless of course this transformation had taken place at a very specific moment in history. For example, if the moon had turned into a black hole in July 1969, instead of that's one small step for man. One giant leap for mankind, Neil Armstrong might have had nothing to step onto at all. As a final thought, you might now be wondering about a different twist on the question. What if the moon were replaced not by a black hole of the same mass, but by a black hole of the same physical size as the moon? That would be a whole other story on. Catastrophic one. A black hole with the moon's radius would need to have a mass about 600 times greater than the sun. With that much mass, the gravitational pull would be so immense that Earth, along with the entire solar system, would quickly be drawn into its grasp. In that case, we wouldn't just lose moonlight, we would all fall into the black hole. That would indeed be a final and total lunar eclipse.